Good afternoon, ladies and gentlemen. Welcome to this session of the NUS ISS Learning Festival, where we'll talk about explainable AI for health tech. My name's Adam, and I'll be covering the first session of this presentation. Now, without further ado, I'm going to proceed straight into the presentation. Now, as the title implies, we're going to be talking about artificial intelligence with particular focus in the health tech area. Now, it is important to first gain an understanding of what artificial intelligence means. I have copied a definition, and it is showing that artificial intelligence, which is coined by John McCarthy in 1956, refers to the simulation of human intelligence processes by machines. Now, I'd like to draw your attention to the fact that this was a definition that was made back in 1956. In other words, artificial intelligence is not a new concept. It has been around for quite some time. Of course, having said that, whatever technology we have back in 1956 is very, very different today in 2022. Now, today, when we talk about AI, it is usually referred to as an umbrella term that encompasses everything from robotic processes, automation, to actual robotics itself. And you might be wondering, this is actually quite a wide field. It is indeed. And we are going to explore some of the nuances today in this session, again, in context of health tech. When we talk about AI in current times, it usually refers to the ability to perform tasks such as identifying patterns of data more efficiently than humans, without the limitations of the human physics. This will enable business to gain more insights out of their data. Now, here's the thing about AI in general, about artificial in general. When we talk about AI, it's really like a box of chocolates. You really never know what you're going to get. So you can have actually different professionals coming together talking about a very specific topic in AI. And you'll come out with, different semantics, if you will. They'll be talking about different aspects of the same thing. This is one thing, this is one aspect of AI that we're trying to address, again, with this, in this context, in the area of health tech. Now, let's take a look at AI in real life action. So I have taken this particular screenshot. It's slightly dated, but the overall concept stays true. And it's titled, Artificial Intelligence Struggles to Tell the Difference Between Fried Chicken and Labradoodles. So I'm going to show you what that means. Now, if you look at the picture on the screen, it is blatantly obvious to you and me that it comprises of two different objects. One, labradoodles, two, fried chicken. However, to the computer, when you run an artificial intelligence program to it, it does get confused. And it's not just between labradoodles and fried chicken. We have other examples that I found off the internet. Case in point, the second photo shows duckling or plantain, or the third one, paktil or cinnamon bun. Now, why is this so? Because when a human look at it, we're able to refer to things in context and also background memory. Now, this is something, context especially, that is difficult for modern AI solutions to grasp. So, how does this translate to the world of health and healthcare? Um, so I have an example here where if you were to process medical images using artificial intelligence, you really have to specify what is it that you're looking for. So case in point here, the example is looking at skin's lesion versus an MRI that's looking at brain tumors. Again, for a human being, for physicians, a medical doctor, or a radiologist, a medical doctor who is specialized in looking at images like CT or MR, or even a dermatologist looking at skin lesions and what have you, this is blatantly obvious. There is two different subjects. But when you try to process it through artificial intelligence without giving context, the solution will sometimes get confused. Why is this so? Well, there's a concept I'd like to introduce to all of you. It's called autistic savant. Now, currently, AI systems have this syndrome, if you will, autistic 7. What does that mean? It's actually referring to a condition in which a person demonstrates one or more profound capacity, ability, far in excess of what would be considered normal. This could be referring it in a good way or a not so good way. Yet often also has significant deficits in other areas of brain processing. So to illustrate it in context, you have high functioning individuals in a certain area. So they could be really good at math, really be able to do fast calculations and what have you. And for that same person, maybe socially awkward, may not be able to do or process some of the everyday daily tasks in what a normal person would be doing. So this is where the extreme aspects comes in. They are very good at one aspects of thing in their life and not so well and slightly below average in other aspects of their daily life. This is autistic 7. And this is exactly what modern AI solutions are like. Because once you train the AI solution, it can be incredibly efficient in a task like recognizing cats or as specific animals, playing computer games, specific computer games, but there is no centralized neural network that actually correlates everything. That you can actually train them to identify objects and images and play games at the same time. The keyword is and. They are unable to do multiple things well at the same time. One thing at a time, fantastic. Multiple, not so. So my example to articulate this would be Google's DeepMind. So in 2015, Google built a solution called DeepMind, where it could beat 49 Atari games. Now, this is definitely a great achievement, but here's the catch. Each time it is trained to play that game and it needs to move on to the next game, you have to retrain the system. So it literally forgets how to play the previous game and then it moves on. Now, can the system try to play all games at the same time? No. So you have some intelligent ways to do it. You can actually train multiple instances of the same program, and then maybe you do this 49 instances, but not one instance where they can actually play all 49 games at the same time. Every time they learn, they have to unlearn all the previous rules. So think about it and translate this in a real life setting. You cannot have the AI solution to be trained to do one specific thing at any one time and then applied in a clinical context because you're trying to utilize that particular program to help you find the diagnosis that you may have missed out. If you're able to actually articulate in the first place what you're trying to look for, you don't really need that solution, do you? Moving on further, in addition to autistic 7, there's also a issue of using artificial intelligence in healthcare, particularly subject matter. So the example I have on screen is a picture where a snake is biting a fish, and the caption say that a brave snake is saving a fish from drowning. Now, you and I would know that this is not true. In reality, the snake is trying to eat the fish, just went fishing, got a fish. Now, but you show this to a young kid who has no pre-knowledge of how snakes and fish works, they would think that the captation is true. This again illustrates another limitation in AI where you actually have to train the solution to understand the subject matter. And training AI solutions to do clinical diagnosis can be challenging. Not impossible, but it can be challenging. Another example I have here, which is taken from a real life newspaper cutting, it says that statistics have shown that teenage pregnancy drops off significantly after the age of 25. Now, from a statistics point of view, this is accurate. But if you go by the definition of a teenager, regardless of what country you go to, it wouldn't exceed 18. So by the contextual knowledge, when you apply to statistics, this actually falls false, right? So this is where understanding the subject matter is extremely important when you try to apply AI into healthcare. It is not as simple as putting in certain rules, but there's also an art to it. It comes with experience. Now, Another issue that we have with regards to using artificial intelligence in general will be something what we call performance versus competence. Now, I have an example here. It's a bit wordy, so I'll let you read it while I explain it. So imagine you have a particular photo that shows people playing frisbee in a park. Now, when you and I look at the picture in context, you're able to infer and draw conclusions. So, for example, what is the shape of the frisbee? Roughly how far do you think the person can throw the frisbee? Because there's a statistics are shown, in sports, what is the limitation and possibility? Now, can you eat a frisbee? These are simple stuff that because we're able to draw on prior knowledge and context to actually interpret the image. Now, can a person eat a frisbee is subjective. If you have a cake that is made to look like a frisbee, of course you can eat it. But in general circumstances, you can look at it and you know that it is actually not a frisbee. It just looks like a frisbee. But if you put it into this particular example I have, unless you tell the AI solution that this is not a frisbee, it will assume that it is, and it wouldn't be able to tell you whether you can eat it. Now, having said that, some people might say, hey, Adam, actually, you can actually start labeling stuff. Yes. But most common labels, the typical type that you see when we try to label images for AI analysis, is very generic. So for this example, you maybe have label as people playing frisbee in a park. This is not going to help the AI solution to help answer all these questions that is posed to them. So this is another issue that we have with artificial intelligence. Now, again, they're very good at doing one thing and one thing only, but you have to actually tell them what to do. This sometimes contradicts what we are trying to use it for in the world of health and healthcare. We're trying to use it to augment and help us in our diagnosis, looking for things that we don't know. So this actually is contradictory. Now, the above that I shared with are some of the so-called limitations of AI that we currently see when we try to apply it in a real-world context. I would also like to talk about healthcare data for AI. So as you will be aware, data is really the crux if you want to do analytics or artificial intelligence. Without good data, you're going to get, not a good result. So garbage in, garbage out. Now, here's the thing. Normally, when you try to do artificial intelligence of any source for industry other than AI, you collect the data first, and then you analyze it, and then you try to draw patterns. So that's the usual regime. And you can do that. Let's say if you're doing a shopping cart, you try to analyze a shopper's behavior, what are the usual stuff they buy, and you try to interpret that data, draw models. That's great. It is really a post aspects of things. In healthcare, it is actually not ethical for you to wait for patients to die from symptoms. Then you collect the data, then you analyze it. That is just simply not how healthcare works. So we have the situation where we try to get data. So you can actually apply it to the ongoing COVID-19 pandemic. When the pandemic actually first happened, a lot of people are saying that, hey, why can't we apply medical model? Why can't we apply big data, analytics, AI, and try to predict how COVID will actually proceed, areas of outbreak, etc., trajectory. So it was very hard, and some scientists did try to do it, and people start complaining that hey, AI doesn't work. But what they fail to understand is that we were trying to do AI back then with little to no data. So your analysis is going to be very far off the track. So this is again something that's a little bit different from healthcare and the other industries. You really can't wait for people to literally drop off and die, and then you take the data and analyze it. But usually when we try to do AI in health tech, in healthcare in general, we will assume that we have all the data inside our electronic medical records, clinical data, warehouse, etc. But you think of the dilemma. We're trying to find out things that we don't know. We don't know what we don't know, trying to find out about it, but we assume all the data is actually available inside our electronic medical record system. That actually doesn't work because to actually find out the unknown, you need real good data. We don't even know what data to capture in this case. So it's really Einstein thinking. So when we have incomplete data, when we try to extrapolate, you have a situation where things are not as accurate as it is. To illustrate, I have a cutting which I've taken off the internet. It's from two different sources. One is from Forbes, and the other is from NASA, describing the same event. So from Forbes, it says that mysterious space debris hits Earth on Friday the 13th. Very nice, catchy headline. In reality, NASA has more information. Okay, so it says that it's actually certain equipment re-entering the space atmosphere. Same thing, similar data, no context, or incomplete data. So you try to extrapolate, and you have very, very different conclusion. So as I mentioned, and in healthcare, we cannot go by the normal trajectory where we actually intentionally collect the data and then wait for people to fall sick. Then you collect the data and you try to analyze it because of medical ethics. Simply doesn't work the same way as other industry. Now, a few other points, just to put everyone on the same page. Some other concepts would be causation versus correlation. Now, this is a very important topic, very sensitive and important topic when we try to apply artificial intelligence in healthcare. So as you're aware, artificial intelligence, we use a lot of machine learning, and these are usually black boxes. What does that mean? We run things through an algorithm, and we don't exactly know how the algorithm process the information. So we just get the end result, and we try to correlate and see whether it works. On the normal circumstances, when you look at it, as long as the results correlate, chances are there may be some relation. But as you know, in science, causation doesn't cause correlation, right? So the example here I have is that some researchers at Virginia Tech created what is essentially eye tracking systems for a neural network, which records the pixel of which the computer looks at. So when the researchers show the solution, the AI solution, pictures of a bedroom, and they asked the solution, what is covering the windows? And the results actually make sense. But when you did deeper, what happened is that instead of looking at the windows itself, so you say what is covering the windows, as opposed to looking at the windows itself, they actually look at the floor. And if there's a bed, it actually gave an answer that there are curtains covering the windows. So what happened here is a classical example of the data that we gave to the AI solution was biased in the first place. It just so happened that the data actually has a correlation, but in actual reality, it wasn't smart enough to tell you whether there's something covering the windows. Now, again, if you are unable to uncover what is going on in the algorithm, in the black box, if you will, and you apply this in clinical setting, you're going to have a lot of issues because they're going to make sensible diagnosis at time and just misdiagnose at times, and you can't really put your pause on things. But here's the difference. Here's the reality. Real world expectations of AI, and this is screenshots covered, captured in various aspects over time, various magazines over time. It is very high expectation. We expect AI to do magic. We have people come in and says, Adam, why can't we just scan the person and automatically have the AI program tell us what's wrong? Now we can replace physician altogether. It's not going to happen. Okay, because of the black box and also some of the other examples that I gave earlier on. The real world reality is if I were to present an AI solution to a clinician, a physician, and he make a diagnosis based out of it, there's a high chance that he may be liable. And he cannot, in good conscience, based on his training, make a medical decision where he doesn't know how that particular information or diagnosis is actually drawn upon to. This is where you hear things like, we have clinical guidelines, evidence-based, where there's peer review, etc., and not Google search. We can't just trust information given to us without being able to verify the legitimacy of it. So here's the thing. AI presents a black box method, which no one's exactly know how input A gets translated to output B. And then for clinical staff, healthcare professionals, we're supposed to trust the result, or else we can't actually use it. It then defeats the purpose. Then we don't need it. So how do we actually overcome, and how do we bridge this gap? Well, this is where I'd like to introduce my colleague, Dr. Tan Jen Hong, to come and share with us something called Explainable AI.
Thanks, Adam. Hi, I'm Jen Hong. By now, you should have a clear picture on the challenges of using AI in HealthTech. Many AI works like a black box where no one knows how the AI reaches its conclusion from the provided input. Fortunately, some of these challenges can be partially resolved using a new type of technology. It is called Explainable AI. In the coming sections, we are going to take a look on three main topics. First is a broad overview on explainable AI. Second, the three main types of explainable AI useful in the domain of health tech. And lastly, the issues with the three main types of explainable AI. We know AI techniques such as machine learning and deep learning have an issue with explainability. We can't explain what it has learned from data, although we know how it learns. We can't explain how and why it makes a decision. We can't just simply modify those methods to make them understandable. And unfortunately, most of them by nature are not understandable to us. In fact, they were not designed and developed with that purpose in mind. So, this is what explainable AI tries to do. Explainable AI are some methods that try to produce or complement AI model to make the internal logic and the outcome of the algorithms accessible and interpretable, and making such process understandable by humans. To put it simply, it is a set of methods that try to figure out how those machine learning methods make decisions. But is this sufficient to resolve the issues that we have seen just now? As we will see later, explaining or explanation is a problem beyond the field of computer science. To get AI to explain effectively to its user and its target audience, we need to go beyond just computational methods. We have to understand what forms and explanations. We have to understand how people perceive explanations. Furthermore, we need to understand why and what people seek for in an explanations. And here we have a chart that shows the explainability of some algorithms versus the performance of those algorithms. From the charts, we can see that AI methods such as rule-based model, which is in purple circle, and linear model, which is in green circle, they have the highest explainability, but almost the lowest performance or accuracy in its usage. On the other hand, methods under the umbrella of deep learning, which is in pink circle, have the highest performance, but suffer greatly in terms of explainability. From these charts, we can see that the easiest way to achieve functional explainable AI in healthcare is to use algorithms that are inherently explainable. That means instead of using deep learning or ensemble methods such as random forests, simpler solutions such as decision tree, linear regression model, or other transparent algorithms will give us an AI that is almost directly explainable, although at the cost of performance or accuracy. Of course, this does not imply that complicated and powerful methods such as deep learning should not be used in healthcare. Some experts have argued that explainable AI in healthcare should perform like any other high performance product, such as a car or a laptop, where most users don't know the intricate workings under the hood but can quickly notice when the product is not working correctly. In other words, to explain an AI model, the idea is not to explain the sophisticated calculations behind the model, but to form explanations that matters to users, to provide a venue for the users to interpret the outcome and to understand if the system works or not. Therefore, in the coming slides, we are going to take a look at three types of explanations that are useful to achieve the intended outcome in explainable AI. For the first type of explanations, we are going to use a case studies on heart disease to illustrate the idea. The purpose of the AI is to detect the existence of heart disease in patients. The area of interest, which is highlighted with circle 1, is a XGBoost model. XGBoost is a decision tree based machine learning algorithm based on a boosting framework. The model is trained and evaluated on a heart disease dataset from UCI ML repository. This dataset originally contains 76 features, but in these studies, only 13 features were used to make a simpler illustration. The training and evaluation based on the historical data leads to the generation of models which are deployed in a production environments, which in the figure is highlighted with circle 2. In the actual implementation, when new data comes in, the data is supplied to the deploy model and a explainable AI module. The deployed model produces predictions, and the explainable AI uses the data and the prediction to produce an explanations that can be consumed by medical practitioners to validate the predictions made by the AI model. Let's have a quick understanding on the 13 features of the dataset before we see the explanations made by a explainable AI module. This is how the dataset looks like. And here, only data of 5 patients are shown. Each row denotes the data of a single patient. Each column represents a feature. The last column, condition, indicates if the patient of interest has or has no heart disease. Among the 13 features, some features are straightforward. Some require a bit of explanations. Some do not matter in the model. For the third feature, CP stands for chest pain types. There are 4 types of chest pain at here, from 0 to 3. The higher the number, the lesser the amount of symptoms experienced by a patient. For the fourth features, it denotes the resting blood pressure in the units of mmHg. For the fifth feature, CHOL, it represents the cholesterol level of an individual. For the seventh feature, rest ECG, it signifies if a patient's ECG is normal or it has a ST wave abnormality or it has a probable left ventricular hypertrophy. For the 10 features, O peak, It denotes the amount of depression in ST wave. For the 11 features slope, when the value is 0, it means there is an upward slope in the ST wave. When the value is 2, there is a downward slope in the ST wave. When the value is 1, the wave is flat. For the 12th feature, CA, it indicates the degree of blocking in the 3 main blood vessels in a heart. Higher value indicates larger degree of blocking in the blood vessels. For the last feature, THAL, it denotes the results of thallium tests of an individual. Value of 0 indicates the result is normal. Value of 1 indicates an obstruction in blood flow, even body is at rest. Value of 2 indicates the obstruction passes away as the body relaxes. Here shows a classification output of a patient from the XGBoost model together with an explanation produced by a method called sharply additive explanation. In short, we shall call it SHARP, SHAP. This method, SHARP, basically calculates a mean prediction of the model of interest. The mean prediction is also called a base value. After that, it identifies the relative contribution of every feature that causes the specific prediction outcome to deviate from the base value. So to understand this explanation, we first need to identify the base value, which is minus 0.3918. Now, if for a specific patient, the model makes a prediction with a value higher than the base value, it signifies that the patient is more likely to have a disease. If the model makes a prediction with a value lower than the base value, it signifies that the patient is more likely to be normal. So for this patient, the model output is minus 3.94, which is much lower than the base value minus 0.3918. The patient is likely to be normal. Now we know the model's decision, but what causes the model to make that decision? Or rather, what pushes the model output to be that low? In this chart, the blue arrow or the blue part of the graph represents the forces that pushes the output to be a lower value. And the red arrow or the red part of the graph represents the forces that pushes the output value to be higher. For this patient, the strongest force that pushes the output value to be lower is the feature C8. The value is 0, which means there is no blockage in any of the 3 blood vessels, followed by a thallium test results, which can be seen by the feature THAL, where 0 stands for normal. On the other hand, if there is any feature that pushes the model output higher, it will be slope, where value of 1 indicates that the ST wave is flat. So from SHARP, we can have a better understanding on how model arrives at its decision and what are the main contributing factors to a specific outcome. In this example, we have another extreme case where the outcome is the opposite of what we have seen previously. The model output is 5 0.71, much higher than the base value minus 0.3918. The model has predicted the patient to have heart disease. So what causes the model to make that predictions? We can see that all the 13 features contribute to reach that decision. Or, put it another way, all the features work against the patients. And among all the features CA has the largest contribution. A value of 2 for CA implies that the patient has a pretty severe blockage in his blood vessels. Beyond that, the patient has quite some amount of depression in his ST wave, as told by his O peak feature. His Telem test was also not okay, which can be seen by the feature THAL. These three features were the major factors that lead to the classification. Of course, the other feature also play a part, but the three features contributes almost half of the deviations from the base value. So from these two cases, we can see how explainable AI can be used to explain the output of a model without actually dissecting the inner working of the algorithm. In this example, the inputs to the model are structured data. That is, in simplicity, the data can be laid out in the form of Excel spreadsheet. For unstructured data, such as images, we will need different kind of explanations. To illustrate how we can provide explanations on the decision outcome on unstructured data, we shall take a look at a case study that tries to detect and classify intracranial hemorrhage on CT scan. And in this example, we are going to learn about the second and the third type of explanations useful for HealthTech. This is an overview of the system. The system in the beginning receives slices of non-contrast CT scan on brain. After that, the AI will perform classification on every single size of CT scan. Each CT scan image will first go through a step of pre-processing and then sent to a deep learning models. There are three types of outputs produced by the system. The first output is the predictions of presence or absence of disease in 6 classes. The first class is intracranial hemorrhage, and the rest are the 5 subtypes of intracranial hemorrhage. The second output is called attention maps. This is a type of explanation commonly used for images. It is a heat map that tells you which part of image causes the model to make a specific decision. The third output is a set of image examples in the training data set that is considered relevant or similar to the input slice. This is another type of explanation useful in healthcare settings, explanation by example. Here is one of the outputs by the system. On the left, we have the ground truth, subarachnoid hemorrhage, in short SAH, was found to exist in these slice of CT scans. And the area that leads to the judgment has been labeled by a team of neuroradiologists. On the right, we have the prediction output by the system, which is correct. And we can see that the AI almost uses the same area labeled by the expert to make the judgment. And beyond that, the AI also lists out 9 examples that it thinks are relevant to the class it classifies. Here is another example on the output. In this case, there are 2 types of intracranial hemorrhages found in these slides, and the AI located both, and the attention maps almost overlap with the areas indicated by the experts. From these examples, we can see that the attention map or the heat map can help to inform if a model makes a correct prediction based on the correct features or areas in an image. From the listed similar images, we can tell if the model has a correct understanding on the scene in an image, and this can help to validate if a model has an accurate understanding on a specific disease. But wonderful it may seem, are these solutions practical enough to be actually useful in clinical settings? What are the challenges we will face if we deploy such a system? For explanations such as SHARP, one of the main challenges is that the concept behind the explanations, the diagram, is not easy to understand for those who have no background or training in machine learning. The diagram looks intuitive only to those who have understood the concept of the explanations. And even for those who have understood the idea, the interpretation can be ambiguous and misleading. According to some studies, it is possible to misinterpret the output from SHARP and therefore produce the wrong explanation for the model. And for the explanation by heat map and examples, the system may simply make the wrong decision based on the wrong features and list out the wrong relevant examples, as shown in this case, where the ground truth is no bleeding, but the system has identified intraventricular hemorrhage. But the biggest problem on the heat map lies on this. The explanation may not answer the real doubt. In this non-medical example, the AI classified the image A here as electric guitar. Image B shows us which part of the image leads to the classification of electric guitar, which is the neck or the fretboard of the guitar. On the other hand, in image C, we can see which part of the guitar leads to the prediction of acoustic guitar. Now, the real doubt that requires an explanation from the output is this. Why does the model take the neck region and predict electric guitar instead of acoustic guitar? Unfortunately, the explanation that truly matters is not available, and we have no way to understand why the model makes such decisions. So, explanatory AI for health tech, are we there yet? At this point of time, there are technologies available in this area. There are studies and development going on to look into how useful and effective they are and what can be done better. But in general, the explanations provided by the algorithms are designed to explain how some features in the data lead to the conclusion made by the AI, and such an explanation may not be useful to clinicians or the target audience. More research is still required to understand what kind of explanations people are looking for in the context of health tech. Currently, the technologies generally produce a one-size-fits-all kind of explanations. and these explanations are unlikely to be truly useful in clinical settings. We believe more research and development is required before we have a mature explanatory AI for health tech. Thank you so much for your time.